Okay, so right? Ashwin gave us, I think, a great lecture with a lot of theory insights, and then we'll go back the slides without equations. So here's the lecture 2, and I will continue the discussion of these two-dimensional magnets and show you what we can do with it. So like I say, mainly we're going to focus on these the heterostructures. But initially, I'm going to show you how we can control these two-dimensional magnetisms, right? And use electric fields. Then I'm going to talk about the example I'm pretty excited about is the spin-lattice coupling effect in the systems. Then the last part I'm going to show you is how to use these proximity effects to control the spins, pseudo spins, and also hopefully the last part I'm going to talk to you about how to control these Carroll edge states in topological insulators. Okay, so here's just a quick recap, right? In the morning, we talk about the chromium triiodide. It's a layered antiferromagnetic insulator. And what it means is, for individual monolayer, it's ferromagnetic, and the interlayer coupling is antiferromagnetic. So this gives rise to these spin flip transitions, right, as we sweep the magnetic field. And I mentioned this example with tunneling junctions. We can measure the tunneling current as function of a magnetic field for these 4 particular devices with 4 layers, right? And we have these intermediate plateaus showed up. And for the top panel, it's co-rotation signals as function of magnetic field. So basically, the correlation is for this particular state, the magnetization M is equal to 2, and corresponding to this intermediate state. And for this magnetization M equal to 2, there's 4 possible configurations, okay? Right, with 1 layer pointing down and with the other 3 layer magnetization pointing up. So the key is this minority layer, right, can be at the top or can be anywhere in the middle or can be in the bottom. So the total magnetization is the same for these 2 states. They sort of, in terms of magnetization, they're degenerate. However, if we look at if we consider the system favors interlayer antiferromagnetic coupling, right? So we can see the top 2 states, there's only one interface which is antiferromagnetic, and the bottom 2 states actually has 2 interfaces, is antiferromagnetic. So if the system favors antiferromagnetic coupling, then the bottom 2 states we should have lower energy than the top 2 states. Right? That's just a logic thinking. Then we can focus on these 2 states at the bottom, which has lower energy, but also energy degenerate. So for these 2 states, we call them bistable states. And in a magnetic field, a challenging task is how to realize control or switching between different bistable states. The challenge is mainly coming from its difficulty of applying electric fields in a conventional magnetic system, because in a conventional magnetic system, they usually have it's a metallic magnet, okay? When the system is metallic, it's very difficult to have electric fields go through the system, right? Because metal is going to screen the electric fields. That's the kind of technical challenge here. So what we have here is that's different because it's an insulator, right? It's a atomically thin insulator. So you can apply a really large electric field actually to switch the magnetizations. So that's what I'm going to show you. So even though these 2 states are degenerate in terms of magnetizations, but if I apply a current or electric fields in these directions, now you can see this degeneracy actually breaks because the direction now is determined by the electric field or current, right? Now you're looking through these directions. These 2 states are not the same anymore, all right? So if we can, now what we can do is this is another example with this 4-layer tunneling junction. Now I apply the magnetic field and measure the tunneling current. Now you can see initially, right, if you remember, there's a plateau which 1 states. But for certain devices, actually I can have a plateau with 2 different levels, right, for these intermediate states. So these 2 different levels are already corresponding to there's 2 different states here. So these 2 different states is the one I just mentioned to you, okay? Then this is just a sort of a hint. We do have these two different bistable states, and there's a chance we can have them both of them accessible by the measurements. To realize the control, so what we do is we make these dual-gated 4-layer chromium triide junctions. It's actually not the simplest device to make, right? So in the middle, we have these 4-layer chromium triide, and we have a monolayer graphene at top and bottom as a tunneling contacts. So here, monolayer graphene is very important because not only it can act as contact, but monolayer, the denser state is low, right? So the electric fields can still penetrate through. Therefore, we can control the magnetic states, use electric fields or dopings. So at top and the bottom, we have a two gate, right? The top we use a graphite gate. The bottom actually we use silicon dioxide gate. The reason for the top is graphite because we also do optical measurements. So we want the top gate is transparent. Okay, so this device, right? We apply the electric fields, through the samples. Then we measure the tunneling current. And here I'm just going to show you 3 examples. The bottom right, what I have here is the map of the gate voltage, right? This vertical axis is the top gate, and the horizontal axis is the bottom gate voltage. And these red dots just means the top gate is 2.4 volt, and the bottom gate is 0 volt. Okay, and in these conditions, then I measure the tunneling current as function of magnetic field. Then you can see there's only one plateau, right? So one state, and this state is corresponding to what I draw here, right? Okay, the minority layer is in the 3rd layer. Then I can change my gate configuration into these particular dots here, okay? Then now you can see there's 2 states showed up, right? So what it means is we break degeneracy between these 2 states now, and one plateau is corresponding to these particular states, and the bottom plateau corresponding to these states. And I can continue to sweep my gate into this corner. Now what we have is one plateau again, corresponding to these states. So by combining these 2 gates, we actually can access different magnetic states. So we can switch, right, the which states we like to get. And here just another examples of these 2 states, right? One is the high current plateau, the other is the low current plateau, depends on the voltage applied to it. Now what we to do is we can just fix the magnetic field and continuously sweep the gate voltage, right? Previously what I showed you is we fix the gate voltage and we sweep the magnetic field. You can see there's 2 states. Then what I can do is I can just fix my magnetic field at the particular number. Then I'm gonna sweep my gate voltage. Okay, so we start with this particular state, and then I sweep the gate voltage. You can see the current, increase, decrease. But this corresponds to switching from one state into the other state. And I can sweep the gate voltage back, for examples, right? And this corresponds to switch the states back from this state to the other state. And that's large hysteresis curve here, right? This hysteresis curve corresponding to the magneto-electric coupling effect. So this is just one example. We switched the magnetic states between 2 bistable states. And we can also switch the magnetic states from one state to the other very distinct states. So the example I'm showing you here is for bilayer chromium triide. So for bilayer chromium triide, right, remember I showed you, is the interlight coupling is antiferromagnetic. So there's 2 antiferromagnetic ground states, right? So these 2 states is still, they are kind of a bistable state. But if we apply magnetic field, and this field is large enough, gonna drive the bilayer from these antiferromagnetic states into this fully spin polarized state. So we have this spin flip transition here. Okay. What we have is now we make this dual gated device again, right, with bilayer in the middle, and we use a graphene as a contact. Then top and the bottom we have 2 gates. In these particular examples, then we measure. What I show you here is a co-rotation intensity plot as function of gate voltage and also magnetic field, right? The vertical axis gate voltage, the horizontal just magnetic field. So what you see here is once we sweep the gate voltage, you can see, right, there's a slope here, okay? So the blue color and the red color corresponding to a large co-rotation signal. And in the middle, right, this blank just means the co-rotation signal is small because it's in the anti-ferromagnetic state. And then each point here represents a spin flip transition. Now what you can see is that the spin flip transition, actually, the magnetic field, right, for this spin flip transition can be controlled by applying this gate voltage. So for example, if I just take I fix my magnetic field at a particular point, a particular magnetic field, right? For example, I select 3 magnetic fields, then I measure the co-rotation signal as function of gate voltage. Okay, so clearly the co-rotation signal was small, corresponding to a anti-ferromagnetic state. Then at large gate voltage the co-rotation signal is large, becomes a ferromagnetic state. Okay. So this is an example, we can use the gate voltage to drive the magnetic states, right, to switch it from an anti-ferromagnetic state to a ferromagnetic state. But for the measurements I show you here is we still need the magnetic field to help this process. So the other group, the King Van Mack and Jay Chan, they also did the similar measurements, but in that device they're able to apply even larger gate voltage to the samples. So from that data, you sort of can extract the interlag coupling J, right? Basically, you can see the J actually keep decreasing. The positive J here represents anti-ferromagnetic coupling. Okay, so you can see at the very large gate voltage, the J indicates the J actually becomes negative. So the other is the anti-ferromagnetic interlag coupling becomes ferromagnetic. Okay, so this it's an indication here. Okay. And if the device can be even better, if we can apply even larger field, I think this switching will happen. Okay. The other pretty neat example here is we know for anti-ferromagnetic states, right, the co-rotation signal should vanish because the net magnetization is 0. So, however, what we can do is we can apply a net electric field perpendicular to samples. So, as long as there's net electric field, then we measure co-rotation signal, as you can see. Actually, the co-rotation signal is increased as we tuning this gate voltage. Okay, so there's a linear response to the co-rotation to this gate voltage. So this sort of electric field induced magneto-optical effect. What's interesting here is we can prepare which states, which anti-ferromagnetic states we have. For example, in this case, I prepare the states into the top layer magnetization pointing up, the bottom layer magnetization pointing down. Now you can see the slope is negative, okay? Then I can also prepare my states with top layer pointing down and the bottom layer pointing up. Now you can see is the co-rotation as function gate voltage, now the slope actually is positive. So exactly opposite to the other states, right? So even though these two states have same magnetizations and we cannot tell which is which, but for these measurements actually by looking at the slope, by looking at the sign of the slope, we can actually distinguish these two states. So the slope, the amplitude of these two slopes is actually exactly the same with each other, but the sign are opposite because there's two different time reversal of each other, basically. Okay, so we're gonna go back to this electric field control in just a few minutes later. But I want to spend a little bit more time talk about these spin-lattice coupling, these kind of new effects
What is the mechanism? You can use the electric control the magnetism.
Yeah. So the key words here is once you have electric field, you break the inversion symmetry, and plus the time reversal symmetry breaking. Then you will have this electric field induced co-rotation effect. Yeah. So the details actually, let me see if I said it here. The detail actually explained in D. Xiao's 2016 PRO paper. Yeah. So first of all, let me just cover the basics of Raman scarings. Okay. In a solid state system or in the molecules, right, there are always vibrations, and if the infrared light is in resonance with, for example, matches this phonon frequency, and if the phonon is polarized, okay, means it's a dipole, right? Then light can directly absorbed by these lattice vibrations. So these are called infrared absorptions. Then if the light incident on the material system and scattered at the same frequency. The blue is incoming light and the red is a scattered light. If the incoming and the scattered light has the same frequency, then we call this as really scattering. Okay, now the third example is now we have incoming light. Then the light is going to transfer energy into this material system, basically going to scatter by a phonon. Okay, so we emit a phonon into the system, then the scattered light will shift it in terms of frequency. So the frequency difference between incoming and the scattered light, it matches a phonon energies. Okay, in this case, we call Stokes-Raman scattering. Basically, a photon interact with the lattice oscillation and give the energy into the material heated up by emitting phonons. Then there's the opposite process. This is called anti-Stokes. Anti-Stokes is the incoming light actually absorb, or borrow a phonon from the lattice. Then the energy increased. So in this case, right, the energy difference of the scattered light to this incoming light matches the phonon energies. Okay. And this process can be used, for example, for solid-state cooling effects, because right, you take a phonon, you sort of reduce the vibrations, you cool down the systems. So again, right, we have these mainly, we have the infrared absorptions, we have the Stokes, Raman scattering, and the anti-Stokes. And for each process, they have depends on there's a particular Raman optical selection rules, and depends on the symmetry of the crystals, and also depends on particular oscillations we're talking about. So now let's go back to these monolayer chromium triode. Right? Monolayer chromium triode has these D3D crystal symmetries. And for these 3D crystal symmetry, I just write, I decompose the irreducible representations, right, into these, basically I decompose these representation into these irreducible representations. And this represents, what the phonon you can have in the systems. And by looking at these rep, because the crystal itself has inversion symmetries, right? Then only those modes has inversion symmetry can be Raman active, okay? Because the crystal itself has inversion symmetries. Then we look at the 6 classes of these rep, right? There's a 6 class, from A to A, 1E, and there's AU, A2U. So there's 6 classes of them. You can see only 2 A1G and 4 EG, they're inversion symmetric, right? All the other modes, 2G or A1U, A2U, and EU, they're inversion asymmetric. So we only have 6 modes, they are Raman active. And here just a very simple analysis. And all these 16, all these 14 actually phonon modes already calculated by this paper, and they basically give you a very nice cartoon, shows what is lattice oscillation corresponding to each mode. What do we care about? What do we have for this Raman active one is these 6 of them, and they also calculate what is the phonon energies, right, corresponding to each oscillations. Okay, so we'll go back to these, and our experiment is we're looking at these Raman spectra and trying to understand these spin-phonon coupling and look for what is new in these 2-dimensional magnets. So first, we look at the Raman scatterings at the temperature of 60 Kelvin without applying magnetic field. And for these, the measurement is there's 2 geometry for it. One is called XX, means the incoming light, the excitation laser, and also the scattering light, they are polarized in the same directions, okay? They're linear polarized. Then there's another one, which is called XY, means that the excitation and detection is orthogonal polarized. So for the XX, it measures the fully symmetric mode. Basically, if you think about Raman tensor, right, is a matrix, okay? Then this XX is measure the diagonal term in the Raman tensor, and this XY is measure the off-diagonal term in the Raman tensor. Now let's focus on these 2 A1G mode, which is fully symmetric mode, as indicates, right? A means it's fully symmetric. 1 and G is also the same. So for this particular mode, and you can look at it, right? Basically, it dominates by these XX channels, and the XY channel is strongly suppressed. This is consistent, right? Because A1G means it's a fully symmetrical mode. What it means is the Raman tensor should be in the diagonal term, which is the XX channel. Okay. Now let's cool down the sample, right? Here just another way to present it. In a 60 Kelvin, when we measure the mode, there's no magnetizations. So let's cool down the sample to 15 Kelvins. We do the co-rotation measurements. You see hysteresis means that's a magnetic orders. Then let's look at these Raman again, right? In these X and XY channels. Now you clearly see, well, there's a very strong signal in the XY channel. Basically, there's off-diagonal component coming into play. The other thing about it is, so this 128 wave non-peak, right, is no longer has this A1G symmetry because A1G is fully symmetric. You can only have a diagonal component. Okay. So somehow, once we introduce this magnetic order, this off-diagonal term come into play. This is kind of easy, and if you think about it, it's not too difficult to understand because when you have a magnetic order, what it means is if you think about the conductivity measurements, right? If you have a magnetism or time reversal symmetry breaking, you should have an off-diagonal term. Then you can see these Hall conductivities, right? Just Hall component, in the transport measurements. So this is a similar concept in this Raman tensor. When you have a magnetic order coming into play, you will have to introduce a similar type of Hall component in the off-diagonal terms. So that's why you can see these off-diagonal contribution in this XY channel in the Raman scatterings. What's interesting is, remember, right, when we measure these magnetic order, we always say we do co-rotation measurements. You shine linear polarized light, and you look at the rotation angle of this linear polarization, but the same frequency. Now the feature I'm gonna show you is actually we can also look at the similar co-rotation effect, but in the inelastic scatter light. Basically, the light is coming out from different frequency, right? They interact with the lattice, either emitting phonon or absorbed phonon. So let's look at these data. First, look at the 60 Kelvin. So excitation is horizontal polarized. Then we measure the linear polarization. We basically do these linear polarization resolved measurements for the inelastic light scattering. You can see, the Raman scattering is in the same polarization as this excitation polarization. So this is consistent with A1G mode. But what's surprising is, now I do the same measurements at the 15 Kelvin when there's a magnetic order. Okay, now you can clearly see the linear polarization actually rotates away, right, from these excitations. And this is with magnetic order pointing up. Then we can also flip the magnetization pointing down. Now you can see this rotation angle is going exactly opposite directions. Okay, and this rotation, we can basically map out this rotation angle as function of temperature. It clearly correlates with this magnetic order. What I want to emphasize is this rotation angle is quite large. It's 40 degrees. Okay? This is actually a remarkable number because co-rotations usually only order milli radius. At least 3 orders magnitude smaller than these, even for very large co-rotations. So this kind of magneto-optical effect actually in this system is remarkably large. And I won't go into detail of the theory, but because we don't even have a macroscopic theory, what I'm going to give to you is a very intuitive understanding, right? As I mentioned to you, if you look at the Raman tensors, right, the diagonal term is give you these basically give you these XX channel signal, but in the off-diagonal term, it's like a Hall conductivities. So in this case, right, because of magnetization, we can manually putting a term which is proportional to these time reversal symmetry term. For example, we say H. You can think of it as magnetic field or magnetizations. So once we have these Raman tensors, then we can look at the light scatterings, right? All we need is we put in the incoming light represented by 100 means it's X polarized, and in the scatter light, it's cosine theta, sin theta 0 means theta just means the rotation angles, right? If theta equal to 0, just means it's X polarized. If theta is 90 degree, means it's Y polarized, okay? Therefore, we can look at the scattered light scalar light just a modular square of these two initial polarization, final polarization, and with a product of these Raman tensors, right? So let's look at these AG symmetry first. As I mentioned to you, for AG symmetry, the Raman tensor only have these diagonal term. So from here we can get the polarization just look like fully A1G symmetries, right? In the same direction as the excitations. Now we can look at the anti-symmetric mode, which is in the BG symmetries, okay? And only the off diagonal term is here. Then we do the same, very simple calculations. You get these numbers here, right? D times sin theta, the modular square. Then because here we only consider the off diagonal terms, so it's exactly basically 90-degree rotates compared to these excitation polarizations. Now in these measurements, right, we have both diagonal term, also off diagonal term. So this is basically it's a combination effect from both channels. So therefore, depends on the ratio between these off diagonal term to these diagonal term, we can have the rotation angles, right? As I show you in our measurements, it really depends on what the number we choose for these matrix element. Okay. So if AG dominates, then the rotation angle will be small. If it's BG dominant, it means the off diagonal term dominates. We have rotation even long, a little bit larger, than that, right? Okay, so this is the effect we talked about for the monolayers. Now let's go to bilayer. And in the bilayer, first of all, what I show you here is the XX channels, the 15 kelvins, okay, without applying magnetic field. Then we see a peak at the 128.8, so this is the AG mode I was talking about. So now if I look at the XY channel, there's a new feature appeared, right, at the different frequencies in the off-diagonal channels. That's interesting. Now, if I apply magnetic field to fully polarize the spin states, okay, now you will see this new mode actually disappear, right? Now they can only show up in these AG channels, okay? See? So in the AFM state, we have a new mode, and in the FM state, this new mode vanishes. Oh, the other thing about it is this mode actually shifted and overlap with this AG mode in the XX channel. So we can do a little more careful measurements. The top is the co-rotation measurements, tell us what is magnetic states we have. And the bottom is the Raman scattering in the XY channel as function magnetic field. It's also intensity plot. So clearly, right, these two, there's a very sharp switch when the spin flip transition happens. Okay, so this is kind of remarkable actually. We can control the magnetic order, then to control or switch a Raman scattering mode. Right? And this only affects these XY channel, but doesn't affect the XX channel, right? We can also confirm this off-diagonal, this Raman scattering, right, in the XY channel is correlated to the magnetic order. So here I plot this signal in the XY channel as function temperature. You can clearly see, right, it vanishes above the critical temperature. Right. And for this magnetic field, either -1T or the 1T, this XY channel also correlates to the magnetic orders, right? But for the diagonal term, which is XX channel, they don't depend on this magnetic order. So this XY channel is a very sensitive probe of this magnetic order. It's coming from basically the whatever magnetic order we form in the system. And so let me just show you how we can understand this, right? These two I can use for a paper to understand what is Davidoff splitting. So the feature first I show you, there's two peaks. They come from these so-called Davidoff splittings. The idea is quite simple, right? Imagine you have two harmonic oscillators, all right? Two harmonic oscillators, they are energy degenerate. When you put together, then you should have two modes, right? But they are energy degenerate, so you don't see splittings. Then what you're gonna do is you start to put in coupling between these two harmonic oscillators. So this coupling here is interlayer coupling in my van der Waals crystals, right? So once you have this interlayer coupling, you couple these two harmonic oscillator together, then these two modes are gonna split, right? You should have two modes. One is one basically the mode 1 plus mode 2. The other should be mode 1 minus mode 2, right? And the energy difference between these two is proportional to the coupling strength, which is the modulus in the system. Then for these two modes, one is A plus B, one is A minus B. So you can see one of them is should be inversion symmetric, the other is inversion anti-symmetric, right? Basically, the inversion symmetry breaks. So here what I draw is there's two layers, and there's two A1G modes, and they couple together through these interlayer couplings. Then we got these two modes. One is inversion asymmetry, as I show here, right? They go out the phase, right? So they're inversion asymmetry. And this inversion asymmetry becomes Raman active because in our system, right, the crystal structure is inversion symmetric. So if the Raman mode is inversion asymmetry, what it means is it should be infrared active. That's just Raman optical selection rules. Then there's another mode, which is the top and bottom, these two modes, right, they move together in phase. Then this inversion symmetry actually, it's inversion symmetric, then this mode will be Raman active. So the short summary is you have two oscillator, harmonic oscillator, put them together, and you can generate two modes. One is Raman active, the other is infrared active. Infrared active in this case will be Raman silent. Okay. So in the other words, we should not see two modes. We should still just see one mode, right? So why we can't see these infrared active but the Raman silent mode? Well, we have to break some symmetry, right, to see these. So we already talked about this in the morning for the second harmonic generations. The crystal symmetry itself is central symmetric, but once we add these spin into the systems for this layered antiferromagnetic order, right? Once we add this layered antiferromagnetism in the system, you see the inversion symmetry actually breaks. So once this inversion symmetry breaks, then these Raman silent but the infrared active mode now will become Raman active because I already break the inversion symmetry. Then we can apply magnetic field to restore the inversion symmetry. Then this Raman active mode will be silent again because inversion symmetry comes back. So the other way to say it is by controlling this magnetic order, actually we control the Raman optical selection rule, right? By controlling the symmetry of the crystal. All right. So this is exactly what we see. Just go back. We talked about this, right? For these antiferromagnetic order, inversion symmetry breaks. So we can see this mode at the 126 wave number. This is the initially infrared active, but now becomes Raman active. So once we apply magnetic field to align the spins in both layers, the inversion symmetry restores in the system. Then this mode now will become Raman silent again. Well, okay, will be suppressed. Then it vanishes. But the XY channel we see here, just similar to what we see in a monolayer case, right? Because they're always off diagonal term there, because the ferromagnetism in the system. So now we have this unique opportunity here. Is we can control the magnetic order, then we control the symmetry in the system, then control the Raman optical selection rules. So the opportunity we have now is, well, I don't have to switch I don't have to apply magnetic field because I just showed you we can use electric field to switch the magnetic states from this antiferromagnet to ferromagnet, right? Therefore, you can imagine, by use electric field switching these two states, it's equivalent to I use electric field to control the symmetry of my system, right? In the AFM, inversion symmetry breaking, and in the fully spin polarized FM states, inversion symmetry restores. So by just switching my gate voltage back and forth, right, I basically tune the symmetry of the system. Then I should be able to tune my Raman modes, use the electric field. So that's the idea. And again, right, for these measurements, we still need the help of the magnetic field, but we fix it at particular values near the transitions. Then we measure the Raman scatterings first at the gate voltage equal to 0 volt. So we see these, right? It's infraactive, but now becomes Raman active. Then apply the gate voltage to a number. For example, basically you can see now we change this critical field value. So what's happening is now at this particular field, the system already in a ferromagnetic state, right? Now you can see this particular peak, it's already switched off. Right? It's vanished. So basically we can use the gate voltage to switch this Raman mode. So here's just another way to look at it is the top is the co-rotation signal as function of gate voltage for the same sample. The same time we also measure Raman scarings. So you can see once we switch the states from anti-ferromagnetic to ferromagnetic, you'll see this mode initially was strong and becomes weak, and the other lineage, the other peak initially was weak and becomes strong. But these two modes basically switch between each other. Okay. So now I'm gonna switch gear and talk about the heterostructures. So heterostructure, these especially its proximity effects is quite important in terms of to engineer all kinds of exotic phenomena, right? For example, if you put a ferromagnet with top-loading insulator put together, there's a chance you can create a quantum anomalous insulator, for example, right? And that's what the people did. They didn't use proximity, but what they did is they basically doped these top-loading insulator. So that's how you see quantum anomalous, for example. Or you can use magnetization interface with superconductors and with some topology, for example, you may create a Maran fermions, for example. And so, but in the two-dimensional, what's really nice is because of van der Waals structure, right? Then the atomic interface is really smooth. Then proximity effect can be maximized. Okay, especially in the 2D materials, right? The crystal itself actually it's an interface, right? So whatever proximity effect will have a maximum effect. And this has been this similar idea has been explored in use conventional magnets with graphenes, for example. In this particular example is European sapphire, I think, with graphenes. They see pretty large exchange field at the interface. And there's also another example is with top-loading insulator with a magnet, and they show they can control this magnet order, the temperature for the magnet order to form. And another example is you interface a 2D semiconductor with a magnet, and you can realize spin injections. Then you can realize this is spin polarized, okay, or polarized light emitting diodes. The last one to show you is calculation, right? Calculation always the prediction always very exciting. So what they show is this proximity induced this exchange field can be as large as 100 Teslas. That's a huge number, right? All right. So in my lab, we started about 3 years ago. We started to integrate the two-dimensional semiconductors with these chromium triadi. Okay. And the idea is we know these WSE2 really well. It has this kind of spin value physics, and we began to learn what CI3 is about a few years ago. Then we thought is maybe we would like to see these proximity effects. So let me just give you a very quick overview of what these transition metal dicotonates, in case you don't know about it. So for transition metal dicotonates, if you look from the top, for the monolayer, they have these hexagonal lattice structure, just like graphenes. But the difference from graphene is these corners, right? One is collagen, the other is transition metal. So the inversion symmetry actually breaks in the system. And then as this paper points out, when there's inversion symmetry breakings, and what's important is for these Dirac cones that call the Brillouin zones, they actually couple to the orthogonal polarization of the light. For example, for the minus K, they can be excited by sigma minus polarized light, and for plus K, they couple to sigma plus polarized light. So these transition metal dicotonates actually it's a system we can use polarization of light to address individual values. And simply, right, this is a simpler picture. I want you to just memorize for a second is we have two values, plus K and minus K. They couple to distinct circular polarizations, all right? And the data are going to be color-coded. So for plus K, always, coated with red light, and for minus K coated with blue polarizations. And in addition to these valley selection rules, they also spin valley locking effects. So as I draw here, remember, just memorize these. For plus K valley, always coupled to a spin pointing up. For the minus K valley, always coupled to a spin pointing down. Right? So sigma plus light coupled to plus K valley with spin up, and the sigma minus light coupled to minus K valley with spin down. And these two valley configuration, they're energy degenerate because the system itself, right, doesn't have magnetism, so the time reversal symmetry breaks. The time reversal symmetry remains. These two values are protected by the time reversal symmetry. They have the same energies. You cannot tell the light emission. You cannot tell the difference between these two values just by looking at the polarization of the light. However, if you apply magnetic field, you can break time reversal symmetries. Then you can distinguish these two values. For example, here, we apply 5.7 Teslas. Now you can see the light emission from plus K valley will be split from the light emission from the minus K valley. These little splits, energy splits, is a valley Zeeman effect. Then I can map out these Zeeman splitting as function magnetic field, and the slope will give us the G factors of the systems, right? All right. The next is, well, what we can do is proximity effect, right? So the simplest, very naive picture to think about is, imagine you have two electron spins, right? As I show here, there's two configurations. On the left-hand side, on the right-hand side, right? On the left-hand side, these two spins, they point into the same directions, and on the other one is spin pointing opposite directions. So then we know that from quantum mechanics, right? The exchange interaction is going to break the energy degeneracy between these two configurations. Right? It's very simple. Now imagine I put them in monolayer. On top these ferromagnets, right? These ferromagnets assume the magnetization is pointing up. So I represent it with these very large spins. They are pointing up. Now I can shine my circular pulse light to the sample. Remember, sigma plus coupled to spin up, right? And the sigma minus coupled to spin down. So now you look at these two configurations, you will see on this left-hand side, right? On this side, okay. The spin fully excited spin is in the same direction as magnetization, but on the other one is fully excited spin is orthogonal to it's anti-parallel basically to the magnetization. Then due to these exchange interactions, these two systems actually will be energy different, right? So this energy difference, we can resolve it by the light emission from this monolayer semiconductor. Okay, so the signature I'm looking for is I look for the circular pulse light emission. We look at the difference between these left configuration to the right configurations. Okay. All right. So here's just the cartoon of the sample. We have a monolayer WSE2 on top of chromium triiodide, and the whole sample is sandwiched by boron nitride, just protected from degradations. And first we look at the light emission from these two valleys, plus K, minus K, color coded again, right? With the red color and the blue color. The temperature is 65 Kelvin above the Curie temperatures. There's no difference, right, between left and right. However, if I just cool down the sample to 5 kelvins, right, below the Curie temperature, the magnetization is going to form. Then clearly you can see the degeneracy between these two valleys are broken, right? In the measurements, we don't apply any magnetic field. So this degeneracy breaking between these two valleys has to come from these magnetic exchange effects. And I can characterize what's the strength of this exchange field, because I know the G factors, right, for the systems. So I also know the splittings between these two values is about 3.5 millieV. So I know the splitting, I know the G factor, then I can infer the exchange field is on the order of 13 Tesla. Okay. Now let's take another look at these measurements at the different magnetic field. Now it's about close to -3 Tesla. All right. And for these measurements, we can define a quantity, which is the intensity difference between these two emissions, right? Two different polarizations. And we can define the difference, we can define this difference of these two polarizations, and normalized by the sum give us a degree of polarizations of my emissions. Then I can plot this degree of polarization as function of magnetic field. Now you see that's multiple switch, right? So this multiple switch has to come from the magnetization flip of these CI3. The other way to look at it is at each flip there's a clear hysteresis curve here, okay? Each of them. And it's really clean data, right? So what it means is my interface actually is really good. The other important thing is, I want to emphasize again, is what I'm measuring here is actually light emission coming from the monolayer WSC2. And we all know monolayer WSC2 doesn't have magnetism. But once it has this proximity effect, you can see light emission, polarization, everything, right? Has these kind of hysteresis effects. So that means is, you can think of this monolayer WSC2, now it's a ferromagnetic semiconductor due to the proximity effect. Okay? So the other thing we can look at this energy splitting between these two peaks, right? Just the Z-mass splittings. So we can measure the Z-mass splittings as function magnetic field. Again, now you can see these multiple switching behaviors. Okay. And last thing we can look at is the bandwidth of these peaks, right? So we can also plot the bandwidth difference or just bandwidth of cell from these peaks. But here, let's just look at the difference. Now you can look at the difference of the bandwidth also has these behaviors. Okay. I'm gonna talk a little bit about it. What does this difference means here? Okay. So let's just put all these together, right? We have this value splitting, we have this bandwidth difference, then we have these polarizations. They all show these strong dependence on the magnetic field. It has these hysteresis behavior, it has these multiple switching behaviors. And so what the physics behind this, right? As a very simple picture is this coming from the spin-dependent charge transfers. So what that means is the chromium triadi and the WSC2, they form these called type 2 band structures. In this, what matters here is, it means the conduction band, the lowest energy conduction band is in chromium triadi, in this EG band. So then the conduction band in WSC2 has higher energy. But the conduction band at WSC2 is labeled by two values, right? One is plus K, red, the other minus K, blue. And each of them, right, they are associated with spin. One is pointing up, the other is pointing down. Now, assume our magnetization first start with pointing up, and the empty band is EG, which is also spin polarized. Now, I'm gonna pump my system with sigma plus polarized light. So I'm gonna excite sigma plus polarized spin in the conduction band of WSC2. Because there's energy difference, right? These two bands, there's energy difference. Then the electron spin in WSC2 will transfer to the EG band of these CR3. So population transfer. So when this population transfer happens, the net electron population in the WSC2 will be reduced. Therefore, the PO will be reduced, right? Because luminescence coming from the electron hole recombinations. If the total population electron reduced, then the light emission will be reduced. Okay. Now we look at these sigma minus excitations. So sigma minus excitation actually creates a spin pointing down. It's orthogonal to the magnetization, right? Then the charge transfer will be suppressed because these two spins are orthogonal. Wave functions are orthogonal to each other. Therefore, the PO will be stronger for sigma minus emission, right? This is the reason just we saw, sigma minus emitted light is stronger than sigma plus. It's due to this spin-dependent charge transfer in the system. And the other interesting feature is when this charge transfer happens, means there's extra realization channels for electron spins in the WSC2. When you have extra spin realization channels, the bandwidth of the PO peak we see should be broader, right? But for the sigma minus excitation, because the interlayer charge transfer is forbidden or suppressed, the bandwidth will be narrower compared to the sigma plus excitation, which has a charge transfer. So we can look at we can correlate the peak bandwidth with the peak intensity, for example, on the sigma plus excitation, okay? So initially, right, the peak width is broad, and for the sigma plus excitation intensity is, the PO intensity is weak because charge transfer. So charge transfer happens, the peak width is broad. Now the switch happens, now the intensity actually increase, the bandwidth now become smaller. Then again, there's another switch, the intensity becomes weak, but the bandwidth now become broad. And again, there's another switch when the peak waves become narrow, but the intensity now become broad. Okay, so these exactly basically correlate to our understanding, right? As charge transfer happens, the peak intensity should drop, but length will get broader, right?
Excuse me.
Yes.
For the EG orbital,
Mm-hmm.
like why does it prefer spin up? Is that because of Coulomb interaction or who
No,
knows?
EG is so basically there's a five electrons layer, right?
Yeah.
For Coulomb, so EG orbital is the spin. So you can host the 5 spins. So they all the ground states without these the crystal field. So the spin is pointing up. There's a spin down band which is much higher due to exchange interactions. So total you can host the 10 spins. Right, the spin up is here, the spin down is up there due to exchange interactions. That's how you get a magnetization. If EG can have a spin down, then there's no magnetization because exchange field effect. Yeah.
What is the additional feature around let's say 1.8 Tesla, 1.9 Tesla?
You mean this little?
Oh, the additional feature.
This here?
Yeah.
Yeah, I'm gonna tell you a little later. Yeah, we'll talk about this. Yeah. Okay. So again, right? I think this is kind of a very interesting effect because we can use it's analogous to this GMR. Right? GMR is dependent on the spin, magnetization alignment between top and the bottom content. But what I have here is actually I can use my light to control the spins in these semiconductors. Then I can control the charge transfers between these two. So it's like a optical type of a switch, right? Okay. So let me just summarize, right? Exchange effect gives us these various Zeeman splittings, and the spin-dependent charge transfer actually gives us effects on the line width difference and on these polarization of the systems, luminescence polarizations, and each flip corresponding to the magnetization flip here. But the first question that time we puzzle is why we have so many different flips, right? So then we do this imaging of the systems. By looking at the polarization, basically we look at the map of these polarizations, and what we found is, starting with high field, right, we keep decreasing the field, you will see actually there's a lot of domains happening, that's right. This color, different color means different domains. And I can also decrease field from high to low, and you can see these domains again, right? So if I focus on one particular spot, for example, on this spot, you will see once we change in field, the color actually switched twice. So these are the ones that gives these multiple switchings. But if I look at the ones at this spot, the color only switch once, right? So it means I only should see one switch in terms of if I measure polarization of Zeeman splittings. So that's exactly what we did. So for example, I can focus my laser spot at this particular spot. Then I look at my polarization as function magnetic field, then we see multiple switch, right? Because this domain actually will flip twice. However, if I look at this spot again, well, it's close to these domain boundaries, so there's some kind of fuzzy, funny thing going on. I'm gonna go back talk about it later, because it's very difficult to understand here. Then we can look really at the domain boundaries. You'll see actually it's complicated, right? But now you already see since the polarization only change, the sign of this polarization only change once, not twice, like I showed you about. And then here looks like ferromagnetic. We only see the sign switch once. Okay. So we call these two domains. One is weak domain, means you can flip twice. There's a strong domain, can flip once. So this weak strong domain is coming from these basically domain dipole-dipole interactions plus Zeeman energies. Okay. And there's a complicated kind of interaction between all these phenomena. Basically, it's difficult to understand, but I will show you a simple example a little later.
I think even within one single domain, it also shows an inhomogeneity feature.
Yeah, that's right.
This inhomogeneity feature is attributed to the non-uniform ferromagnetism of CRI3 layer or to the inhomogeneity electric of the WSE2 layer.
Yeah, so this inhomogeneity is due to the interface. Yeah, because I'll show you. You will see this much clearer. Yeah. So this is the experiment we did 3.5 years ago, and got us really interested. So the information I have here is for this sample we used the chromium trilayer is about 10 nanometer. So that means there's about 15 layers. make the study is a little more complicated to understand these things. So I'm going to show you another example a little later. Yeah. Okay. Let me see how much time I have.
It's about 20 minutes.
Okay. So let's see how far we can go. So now we have these strong weak domains. So the idea we have is, can we use light to control these domains, right? If I can use light to control domain, I can control this proximity effect. Then you can think about, basically I just need to shine light. Then somehow you can think of the effective magnetic field is tuning by just light itself. So we don't need a magnet. We don't need a superconducting magnet, for example, to do measurements, right? For a lot of measurements, you don't have access actually to the magnetic field. So that's the idea. I'll quickly go through these. Okay, so we for this particular example, identify two domains, A and B. And for these two domains, let me quickly go through these. For domain B is the sign only flip once. We know it's a strong domain. But for domain A, it's a weak domain, means we see multiple sign switchings. Okay, so we focus on these domain A here. All right. Then the next thing what we did is we look at the hysteresis curve here, right? As function of excitation power. So starting with low power, right? There's a stronger hysteresis. Now as I increase the power, you can see this loop actually melted, right? First hint, right? Once we can use the excitation power to control these hysteresis, control basically the spin flip from one to the other states. Then, if we focus on this line, basically you're saying if I starting with these states at the top of the loop at a high field, and actually it's going to go down to the bottom of the loop, means the magnetization actually flips sign. So the way to look at these is, let's go back. So I can look at basically I can plot these polarization as function of magnetic field and the excitation power. You see this 2D map here, right? You see the critical field for spin flip transient is kind of tuned. At least map looks a little familiar with my gate-dependent map, right? It's sort of tuning this critical field, but in that case, I use the electric field or doping. This one, what I'm doing here is actually just use laser power, right? And then we can also say we fix on this particular spot, we fix magnetic field here. Then what I did is we can look at the circular polarized light emission from the samples. And the full microd, you will see, this red color is stronger than blue, means the system is a sigma plus polarized. Then let's increase the excitation power, basically I'm gonna go along this line. So you will see just by simply tuning the laser power, actually I flip the polarization of my light emissions. So means I switch these two light emission from the values. Initially it was the sigma plus dominated, now it becomes sigma minus dominated. All I did is just tuning the laser power. It's equivalent to tuning the magnetic field actually in the system. So here just another map is showing the values event splittings, okay? You can think of this as a map of an exchange field. So let me just quickly, so the bottom one is kind of more important. This is Zeeman splittings, right, as function of the excitation power. You can see the Zeeman splitting initially was 4 millieV, it's positive. Now, as I change power become negative, right, means the sign of this exchange field actually is changed by just simply tuning the excitation laser power. And we can convert this in terms of effective magnetic field. So you can tune the effective magnetic field basically from minus 16 Tesla to about 7 Teslas.
You incident light polarized or not?
Not polarized. Yeah. And we tried the polarized light, see if we can actually tune the magnetic, but it doesn't work. The reason is the anisotropy of the system is too strong. So the angular momentum of light is not enough to flip the magnetizations. Okay, so right, the question is, what's happening here, right? Why Asian light can flip these magnetizations? So that's two possible effects. The simple one always, the first one always a simple one, which is a heating effect. You shine light to a sample, just like you stand on the sun outside, right? If sunshine, you heat it up, right? It's the same thing. We shine a lot of light to a sample, we heat it up. So if you heat it up, then the hysteresis loop will always melt it. Just imagine, you heat up the system above the Curie temperature, then there should be no hysteresis, right? No ionizations. So that's a very trivial interpretation. And to test these, right, we look at the RMCD, which is you can think of co-rotations as function of excitation power. Okay, it does look like similar to each other. Okay, look. What it means is the magnetization indeed actually follows these light polarization measurements, but maybe the heating matters. Now, if I look at the temperature dependence, so I physically warm up the system, not by light, but by just warming it up, right? Now you will see the hysteresis the loop does shrink. However, it doesn't look the same as I increase the power of my excitation light. So what the other say is it's not as simply just a heating effect. I think heating actually plays a role, but not the only effect. It's possible there's a strong photo-doping effect. Because imagine, right, when I shine light, excite the carriers in the WSC2, and this carrier will transfer into the chromium triode. So when the carrier transfer happens, effectively we dope the system, right? So it's a photo-doping effect. So there's two effects coming into play here. One is the heating effect due to the laser excitations. The other is the doping effect due to the charge transfer. So I think the interplay between these two effects that give rise to this phenomenon. All right, I'm gonna switch these. Okay, so there's a lot of questions come up, and let me try to understand, explain to you. You guys are asking a lot of details, right? We also puzzle by all these details. Then what we do is, the puzzle all coming from because we use quite a thick substrate. And then we make new samples. Now we can use only 2 layers or 3 layers of substrate because we know the magnetic states in 2 layer or 3 layer really well. Okay? Then we can correlate the magnetic states into these behavior in the WSC2. Then we can understand all these detailed features. So let's first start with this tri-layer, right? The tri-layer, again, remind you, in these co-rotation measurements, we see these 1, 2, 3, 4 steps, right? And there's 3 spin flip transitions to represent 3 states. Then we can go look at these polarization again, right? You are asking what this little step is, okay? So now we can understand what this little step is. In this tri-layer, first of all, right, the bottom is the light polarization, the degree of polarization in function magnetic field. The top panel just the co-rotation represents the magnetic states, right? So starting from the from the magnetization is fully spin polarized up. And as increase the field, then the middle one flipped, right? The polarization flip up. Okay? When this flip happens, there's a little drop in these polarizations. Then, at this transition, the top surface actually spin down into spin up. Then we see a sharp change of these polarizations. The sign also changed. This is because my magnetization changed, right, in the top surface. When the magnetization top surface changed, then which spin is favored to transfer from WSC2 to CR3 is also flipped, right? Initially, for example, it's a sigma plus. Initially, with sigma minus may be favored. Then later on will be, if I flip these magnetization M here, then will be favored sigma plus transitions. Okay, so light will be sigma plus polarized. Then we can keep doing these. Okay, so these just flip these. Then initially, finally, we reach these states when the spin is fully polarized up. So from these simple measurements, we can tell, we can tell these little fine difference. But the main message is the charge transfer between chromium triode and WSC2 is dominated by the first layer, the top layer, and the middle layer only introduces these little features here. Okay, but the interface layer is the most important. Determines the degree of polarization, also determines the sign of the polarizations. Okay, that's the first technical message. Right. So spin-dependent charge hopping is dominated by the first layer. Now, what a surprise result is, now I look at the Z-mass splittings. right? So top again is the co-rotation. The bottom is the middle one is the polarization as function magnetic field, and bottom is Z-mass splitting as function magnetic field. Now you see something funny, right? Actually, the Z-mass splitting is larger in these antiferromagnetic states rather than in these fully magnetic states. Right? This is kind of surprising. You would imagine, fully, at least for me, intuitively, I would think, it's fully spin polarized, then the Z-mass splitting should be larger. Because in the middle, right, this layer already, pointing in different directions from the first layer. So this was kind of the surprising results for us. And this is trilayer. Then we go back to do the bilayers. So this is another sample image for the bilayer. Right? The left is the co-rotations, just typical for a bilayer. And then in the middle is the polarizations as function bilayer again, where you see a little drop here, just due to the bottom layer flipped, and then the sharp change, the top layer flipped, right? But now you look at Z-mass splittings again, right? In the antiferromagnetic states, actually Z-mass splitting is larger than when the bilayer in the fully spin polarized state. So we can model these systems, right, by considering the charge hopping from the conduction band WIC2 to the valence band of the chromium triiodides. First, we consider chromium triiodide is in antiferromagnetic states. What it means is the spin hopping from one chromium triiodide to the other chromium triiodide is forbidden. So let's set the hopping term to be 0. But the hopping between these WIC2 and the chromium triiodide first layer is represented by TC here, right? So just by solving these Hamiltonian, then we can find out the conduction band energy shift for this WIC2 is proportional to this term, which is T squared divided by delta. Delta is a band offset. So the difference, right? So the key is for valence polarization, right, is due to the spin-dependent charge transfer. So this spin-dependent charge transfer is actually real electron spin hopping. That's a really population transfer. But for the Z-mass splitting, it's an exchange effect. The exchange field effect is a second order, actually virtual electron hopping. So, basically electron go to the, you can think of second order process, right? The electron from WIC2 will go to the CI3, then will come back to WIC2. Okay, so this will give us the exchange. That's a second order process. So what I'm modeling here is a second order process. You can see the energy shift due to the second order process is proportional to T squared divided by delta C. Then now we can also consider in the fully polarized state. Now we can turn on the charge hopping between these two CI3, not represented by this D here. Then we can solve this Hamiltonian again, and we can infer this band shift is proportional to this term. So the difference from previously, right? Basically, we involve this D here now in the denominator. Okay, so in these optical transitions, what I really measure is energy difference between this conduction band and valence band. I'm not just measure the conduction band itself, right? So there's another certain process happening, the charge transfer happening in the valence band. So we can also take into that account to do the similar analysis. We can get another number, which is the transitions from these valence band. Then we can calculate the total energy difference between these ferromagnetic and the antiferromagnetic states, right? By taking the conduction and the valence band difference. So we got numbers. So if we plug in the reasonable numbers in the models, actually we can really infer the Z-mass effect, the Z-mass splitting for these antiferromagnetic states is indeed larger than the fully spin polarized states. Okay. All right. So now I told you basically we have this strong proximity effect between WIC2 and the CI3s, and we can use these. We can use the polarization of the light to tell what is the first layer of this magnetization, right? So simply put, if the polarization we saw, if light polarization we see is CR minus polarized, what that means is the top layer should be spin pointing up, right? Simply, And if the PO polarization is a sigma plus polarized, means the top layer should be spin pointing down. So the polarization of the light indicates, basically it's a measure of the magnetization in the systems, right? Again, CL minus means the top layer spin pointing up, The sigma plus means the spin of top layer is pointing down. So all I need to do is just look at what's the polarization of my light. Then I can measure what is the magnetization of the adjacent chromium triide layer. Then we can look at the bilayers, right? In the bilayer sample we have here, for example, as I show here, the bottom is the co-rotation map, right? So you can see near the field, the small fields, the co-rotation almost vanished, means the system is in the anti-ferromagnetic state. So if I just cool down a sample without applying any magnetic field, okay, just cool it down. First, I look at the co-rotation map. It's at bottom. So you can see the co-rotation map is, the signal almost vanished, right? Because the system is in anti-ferromagnetic states. So net magnetization vanishes. There should be no co-rotation signals. So that's what we see. Now, if I look at the cyclic polarization of the luminescence from WSE2, this is what I got in the top. It's very colorful, right? It's not boring. So you will see this red color, this blue color. As I mentioned to you, red color means it's sigma plus polarized, blue color means sigma minus polarized of light, right? Remember? If the sigma minus means the top layer should be pointing up, the sigma plus means the top layer should be pointing down. So from here, we know, from the color of this light polarization, we know actually the top layer in this red color is pointing up, sorry, it's pointing down, and for the blue means the top layer is pointing up, right? But from the co-rotation map, we know it's in fully anti-ferromagnetic states. So what it means is we actually have domains. We have two domains. Right? One domain is with spin up, spin down. The second domain corresponding to sigma plus is red curve with the top layer pointing down and the bottom layer pointing up. So what I'm really mapping out here is a anti-ferromagnetic, it's a domain structure, but it's a layered anti-ferromagnetic states. So for this red color, it represents these anti-ferromagnetic states 1, and for the blue color, represents anti-ferromagnetic states 2. Okay. So these layered anti-ferromagnetic states, you cannot tell from this co-rotation mapping because it only measures the total magnetization. But combined with these spatial mapping from this polarization, we actually can tell there's a spontaneous domain formed in these anti-ferromagnetic states. All right. And this domain actually can be reconfigured if I apply magnetic field. For example, so I started with, I initialized system into minus 1.3 Tesla, so basically fully polarized spin states. Then I go back to 0 Tesla, right? Initially, left-hand side is a spontaneous polarization map. But once I initialize system, you will see actually most of the domain is gone. Only one left here, right? And I can do the same, just go to negative field and go back to 0. You will see the domain flip signs, but the domain boundary doesn't move for this one. Okay, so it means for some domains, we can reconfigure the domain boundaries, but for this particular domain boundary, the domain wall, it doesn't change. So our hypothesis is actually due to this transfer process, there's always strain induced in the systems. Then the strain will ping the domain wall. All right. So the other thing we did is you can look at the the light polarization from these individual domains, right? Clearly, in the top domain, what I'm showing you here is actually the bottom layer flipped first, because you look at it, right, the polarization only dropped a little bit as the spin flip transition happened. But for the bottom domains, you see, the polarization actually dropped dramatically first. Right? At the spin flip transition means the top layer actually flipped first. So that's the difference between these two domains. So we can all tell this difference by looking at the polarizations of the light. And we can also imaging these domain evolutions near these spin flip transitions. So the top just co-rotation map, the bottom is polarization map near the spin flip transition. You will see they don't flip at the same time. There's a lot of inhomogeneity going on in the systems. It's just due to, again, likely due to the strains we formed due to these, Okay, so I think I will stop here actually. I'll take questions for the last 5 minutes.
I have one question.
Yeah.
In the very beginning of the slides, you show there is a multiple level of resistance But the antiferromagnetic configuration of those 4-layer, is up, down, down.
Yeah, if you're interested, just take a picture of this one. Yeah. These are the at least system people are studying right now published. Yeah. There's a lot of people working on different systems. Yeah, but it's a very dynamic field. So I think it's sort of a summary of this. Okay, you can continue your question.
My question is for this tunneling resistance. Up, down, and down, up, down, down. The resistance seems to be different. So why is it like that?
Because the symmetry is rigged, right?
Those two, two configurations to me.
Once you have the electric field pointing there, right? The symmetry breaks.
I see.
That's just a simple way to think about it. Symmetry breaks. But if you look in details, right? The first configuration is a spin up, spin down, then spin up, right? So the spin polarization, basically the light coming, the current coming goes through the first layer is spin polarized. They immediately hit a filter with opposite polarization. But now you look at the second configuration. The electron will go to two spin filter first, highly polarized, then hit a filter with opposite polarization, right? So these two are very different.
I see. So it's not from AC measurements.
No.
Okay, DC. Any other questions?
You guys all look really tired. you need a break.
Yeah, let's thank our speaker again.